Hello everyone, am I audible? Okay, I hope I'm audible. Hello and good afternoon. I am Sohini, and today I am going to be presenting the work that I have done basically as part of my master's project and a bit of a continuation of that work. So I recently completed my master's from IIT Indore, and this is basically done over there. And these are my collaborators who have very kindly helped me get this done. Okay, so the main idea of the work was to see whether we can use ANN-based emulators as a cheaper alternative to simulations, semi-numerical simulations, when we are trying to do MCMC-based Bayesian parameter estimation. And for that purpose, we decided to pick up two signals, which is where the multi-wavelength part comes. The two signals are C2, which is emitted at 158 microns, and of course 21 centimeter. So these are some of the simulated maps of those two signals. The maps at the bottom are your average H1 maps, which have been simulated by a combination of in-body simulations followed by FOF Hello Finder algorithms, and then the Riya and Yuga set of codes. The top panel is actually the simulated C2 maps. So these are C2 intensity maps which have been generated by basically assigning C2 luminosity to dark matter halos, and these halos have been again generated by n-body and FOF algorithms. So as you can see, the redshift progresses from left to right. So the reionization progresses from right to left. Yeah, so this is what we are going to work with. As for C2, this is what the C2 power spectrum looks like. Now, why C2 is interesting is because it is proposed that C2 can be used as a tracer of star formation rate, and hence as a tracer of early galaxies, source galaxies, which are actually reionizing the intergalactic medium. So to generate a C2 luminosity for each dark matter halo, this is the formalism that we have followed. So the idea is that you can relate the SFR or the star formation rate with the dark matter halo mass hosting the galaxies using a formalism like this, and this can be changed up. Various authors have used various formalisms. And then the SFR can be related to the C2 luminosity using a formula such as the one at the bottom. And this is precisely the formulation we have used to assign C2 luminosities to our dark matter halos. Now, the question is, why do we like to use cross power spectrum? Speakers before me have talked about this in great detail. So, this is just an overview that this allows us to potentially mitigate the effects of foreground, and it also allows us to constrain all three reionization parameters, which are minimum halo mass, ionizing photon production efficiency, and mean free path of ionizing photons, which the C2 does not allow by itself. So ultimately, of course, the aim was to do Bayesian inference, and this is a simple overview of that process. This is your average step in an MCMC algorithm. So for every asset step, a random trial point is drawn, and then the algorithm checks whether that point needs to be accepted or not. If it is not accepted, then the next point is set as the previous point, and we go again. Otherwise, the next point is set as the trial point, and it goes on and on. So this is one of the iterative steps. Now, these are basically the steps that we followed to basically start with our project. Of course, we needed a data set of simulated signals. So we simulated that. Then we split it into training and test set. Then we used the training set to train an emulator model. And once the model was generated, that was used as the theoretical basis for our Bayesian inference. So this is for the C2 power spectrum, which is what we picked up first. This is what the training set looks like. So this has a sample of, this has like 2,167 samples. So there are 2,167 individual sets of power spectrum. So what is happening here is that we are changing the minimum halo mass from one power spectrum to the next. So for every line that you see, there is a different minimum halo mass. And yeah, that is how we have generated this data set, and this is what will be split into two sections. One is training and one is testing set, and that will be used for training the emulator. So as I mentioned, 80% of the data set was used to train the emulator, and this is what we came up with. So we achieved a prediction accuracy of 96.8% from our model. And these plots basically show some of the comparisons of that model. So the solid line on these plots show the simulated data, the simulated C2 power spectrum, and the dots show the emulated C2 power spectrum for the corresponding parameter values. And yeah, this is basically what the emulator this is basically how the emulator was performed. So using that emulator, we moved forward to do a parameter estimation. And this is the sort of result we were getting, which is basically the Bayesian inference framework, or the combination of the emulator and the Bayesian inference framework was not at all able to constrain the parameter anywhere near the true values. So this was quite surprising, and to investigate the reason behind this kind of a thing happening, what we did is we ran the same Bayesian inference framework, but this time with the simulator. So this is a comparison of what happens when we run the MCMC with the simulator. You get the true value as the inferred parameter, whereas when we run the emulator for the same value, you can see that the estimate that the MCMC algorithm throws out is not at all close to the true value of the parameter that we provided. So from those experiments, what we could safely conclude is that simulators seem to be a better option as compared to emulators, at least for signals like C2. And the reason behind that is that the C2 power spectrum is more or less featureless. So the only thing that varies in the C2 power spectrum is the amplitude. As you change the minimum halo mass, the amplitude changes. So the amount of data that is required to get the kind of accuracy that would potentially give us a reasonable result from an MCMC algorithm essentially kills the purpose of building an emulator at all. So it is much more efficient to use simulators for signals like C2. Now, from there we moved on to the next part, which is the C2 21 centimeter cross power spectrum. And these are the steps that we followed. So again, we simulated a bunch of data. We split those into training and test sets. And then we trained 4 different models for 4 different K modes. And after the models were generated, we tried to perform parameter inference. So basically, using the 4 different models, this is the kind of estimates we are getting at this point. So every K mode has a different model, and we used a data set size of 600. So as you can see, it is very evident even visually that the estimates are not very good. However, we've decided to move on with this model itself, because this would be a proof of concept on whether we should whether we should proceed with this at all. So using those 4 models, we use the same kind of parameter estimation framework, MCMC, and this is the kind of preliminary result that we have achieved, where it already shows a bit more promise than the C2 power spectrum or the emulator for the C2 power spectrum. So to summarize, what we have done so far is that we have built an ANN-based emulator, and it was trained to emulate the C2 power spectrum. We have achieved a decent amount of accuracy with that emulator. We have also built 4 separate emulators for the C2 cross 21 centimeter cross power spectrum, and we have also built 2 Bayesian inference frameworks for these 2 signals. And these are the conclusions that were drawn, that in case of C2 signals, simulators are better for parameter estimation than emulators, and for C2 cross 21 centimeter power cross spectrum, emulators show more promise. However, further investigation is needed. So to do that, what we plan to do next is that we would like to improve the robustness of the cross power spectrum emulators, because we suspect that we need a lot more number of samples to get a reasonable accuracy from our emulators, and we might also need to look into better sampling methods and such. We would also like to incorporate ANN uncertainties into into the Bayesian inference framework, which should also help with our estimation. And if that is done, then we could also incorporate realistic observational effects such as noise and such, and investigate the viability of ANNs once that is done. So yes, that is it for my presentation, and I would like to take any questions if you have.
Questions? So these C2 results are really alarming, and maybe it's important to understand exactly what happened there. So this question came up in yesterday's discussion session from Suman about whether it's better to emulate just the statistic or to emulate the full box. What has been done here?
Here we have just emulated the statistic. So basically, when you are training a neural network, the data that you are providing, in our case, was just the statistic.
But then it's how can your emulation report 97% accuracy but still fail at the
that was simulated essentially. The simulated C2 power spectrum.
Sure. But the emulation success is 97%.
Yeah, but that is because of degeneracy.
It's shifting by whatever.
Yeah. It is because of the degeneracy. That's the problem.
Is that right?
That is precisely what is happening. So because it's a featureless quantity, so what happens? Your random walker gets trapped in kind of local minimas, which are not necessarily even close to where the truth is.
But then this is not a problem with the emulation. This is a problem with your inference. You just needed better random walker.
Not so. That's why we tested it both with simulator and the emulator, and it turned out the simulator was working there. So
strange.
That is not
very strange.
Yeah, not. It's not a problem with the random walker. So what we gather is the following. Because if you see the C2 power spectra, it's like a power law and almost featureless. So the alarming thing, people should be alarmed about the foregrounds now, because foreground is also a featureless power law like thing. And when they try to model it using emulators, there are pitfalls potentially. At least this exercise shows that.
But featureless things should be easier to emulate, right?
But what is happening because of the accuracy, if you look at where this sigma of this particular MCMC plus emulator, the sigma or the width is much smaller compared to the other case where that sigma is much broader. So that actually does create the problem.
Okay.
It's too accurate.
I see. Okay, I see. But I'll just to comment that emulation would be important for C2 because ideally you would also want to do cosmological parameter estimation, and also these simulations probably don't match the volume that the C2 surveys will probe. And so I think it would be important to figure out a way of making this work for that. Thank you.
Thank you.
Hi. So I have this question that have you considered using some kind of PCA based method to first know what are the input parameters that actually matter?
No, not yet, because we did this kind of manually. So if I show you, yes. So there are, it appears that there are a lot of parameters that could be varied, right? So we tried varying, for example, alpha, gamma, delta. These are from simulations, by the way. So we tried varying those, and those do not seem to have any effect. Any effect on the power spectrum, any discernible effect. Then we tried changing this model, which is defined by the ALC to BLC2. And what this does is it just changes the magnitude of the C2 power spectrum. So it would sort of introduce further degeneracies. So we have in our analytical expression of C2, we have tried to vary everything that could be varied. And M halo minimum is the only thing that seems to have any physical relevance and any significant impact on the power spectrum. So that is the.
And one more question. So, when you said this 97% accuracy, you are sure that there was no data leakage from test to training data set? Because that seems
Yes.
very surprising. That
Yes. And 97% accuracy is basically the sort of number of points that were predicted correctly, which is traditionally what neural networks, deal with. And yes, we ensured that there was no data leakage between the two.
have you considered taking a larger test set?
Yes. So I trained with. So we have 2,000 plus samples, right? So I have tried training with 80%, 85%, 90% of the total set, and they have similar sort of accuracies. So it doesn't really affect the emulator model or the parameter inference as such. And
and you also tried k-fold algorithm kind of a thing.
Sorry?
Where you basically divide your test and training set in different bins, and then you randomly pick up your test set and then randomly test it on a test data set.
Yes.
Have you tried that as well?
Yes.
The accuracy is similar.
Yes.
Okay.
Hi. So, did you use any normalization technique
Yes.
during the training?
Yes. So basically, the issue with normalizing this kind of signal is that we have to sort of keep it consistent between simulation and emulation. So I had to basically write my own normalization technique to sort of reduce the dynamic range of the signal and the parameter space both. So the first thing that we do is to just use k cube by 2 pi square, that normalization to have a dimensionless power spectrum. And also there was a mathematical normalization that I used that basically reduced the dynamic range of the whole data set to what is acceptable in neural network community, which is 0 to 1.
Okay. So, there is another question. So, whether you check while training, like your training is overfitted or underfitted, did you check?
No, we
metrics?
fixed that. There was an overfitting issue. You must know that I tried this with a smaller data set first,
Okay.
and there were those kinds of issues and such. But yes, in this model, we have fixed that. There is no overfitting or underfitting.
Okay.
So, if no more question, we can stop here.
Thank you.
Let's thank
Thank you
Sohini
so much.
and all the speakers.